Hello and greetings to everyone. Welcome once more to another video in our YouTube channel. So in this video we are going to be looking at the entrance examination into the College of Technology 2021 Mathematics paper 2, question number 1. Alright, this question came from the topic integral calculus, and the question was quite good and technical for some parts. We arrive in those parts, I'm going to lay more emphasis. Alright, the question reads, let I of n be equal to the integral of x to the n times e to the negative x dx, where n is a natural number that's 0, 1 and 2. Roman 1, calculate I0. Roman 2, show that I of n is equal to negative x to the n e to the negative x plus n times I of n minus 1. Roman 3, we use Roman 2 to calculate I of 2. And Roman 4, use Roman 2 to show that the integral from 0 to infinity of x to the n e to the negative x dx is equal to n factorial. Now this is the most interesting part of this question, that is Roman 4. It is the most interesting part of question 1, because calculating I0 will not give you any problem. Showing this is using integration by parts. Using Roman 2 to find I2 is not any problem, but now the problem which requires critical thinking and brainstorming is actually Roman 4, and I'm going to show you why. Alright, so let's begin gradually with Roman 1, which is asking us to calculate the value of I0. Now what's I0? I0 is gotten by replacing n with 0 in the expression of I of n. So our I0 is the integral of x raised to the power 0 e raised to the power negative x dx. Students should pay keen attention that this is an indefinite integral. Alright, so x to the power 0 is 1, since x is different from 0. That's by the domain of definition of the integral and with the values of n. Alright, so x is clearly different from 0, because if x is 0, 0 raised to the power 0 is not 1, it's undefined. So for this integral to be defined, the integral needs to be defined. So x is different from 0, since our n begins from 0. So it means our I0 is the integral of e to the negative x dx, and when we integrate e to the negative x dx, we get negative e to the negative x, and since it is an indefinite integral, we need to add the constant of integration. So in conclusion, our I0 is equal to e to the negative x dx, e to the negative x plus k, where k is a real constant. We are done with Roman 1. Now Roman 2 is asking us to show that I of n is equal to negative x to the n e to the negative x plus n times I of n minus 1. So here we are going to use the concept of integration by parts, because we are integrating two functions and no substitution can work. So to always use integration by parts, we verify if there is any substitution that can work. Now x to the n and e to the negative x have nothing in common. So here the best way to proceed is by using integration by parts. Alright, to use integration by parts, I first verify my proof. My proof is having I of n minus 1, and I know that I of n minus 1 is this very integral, but the power of n of x here is just n minus 1. So for me to have x to the n minus 1, it means I have actually differentiated x raised to the power n. So there we go, we let our u to be equal to x raised to the power n. We differentiate both sides with respect to x, we get our du to be equal to n x raised to the power n minus 1 dx. Now my dv is going to be the leftover function, which is e to the negative x dx. Now to get v, I need to integrate both sides. When I integrate e to the negative x, I get negative e to the negative x. Now integration by parts says that my I of n will be equal to uv minus the integral of v du. Now what is my u? My u is x to the n, my v is negative e to the negative x. My v as well is this, and then my du is this. Alright, so I just fit in their respective positions, and I get my I of n to be equal to the product of u of n and v of the product of u and v gives me this first quantity. Now the product of v and du gives me positive here, because we have our v is, we have a negative sign here, it multiplies with a negative sign to give us a positive sign. Now since du has an n which is a constant, it does not depend on x, because here we are integrating with respect to x. We pull the constant outside, and then we get now the integral of x raised to the power n minus 1 times e raised to the power negative x then the x. Alright, since this is my definition of I of n, it means to get I of n minus 1, I just replace n here with n minus 1. So I get this as my I of n minus 1. So in conclusion, it means that this portion of this term here is represents I of n minus 1. So we can conclude that our I of n is equal to negative x to the n e to the negative x plus n times I of n minus 1, which is what was required to prove. Alright, Roman 3 is asking us to use the expression in Roman 2 and calculate the value of I2. Now this is Roman 2. It says that I of n is equal to negative x to the n e to the negative x plus n I of n minus 1. So what's I2 is just replacing n with 2, NYC n in the expression of I of n. So I2 is equal to negative x squared e to the negative x plus 2i 2 minus 1. The 2 minus 1 is 1, so I2 is equal to this quantity by here with I1. Now we need to get the value of I1. So we do the same thing. I1 is just replacing n with 1 anywhere we see n in the expression of I of n. So I1 is equal to negative x to the power 1 e to the negative x plus 1 times I1 minus 1. But 1 minus 1 is 0, 1 times I0 is I0, x raised to the power 1 is the same as x. Alright, so it means my I1 is just negative x e to the negative x plus I0. Alright, with that said, we can go back and replace I1 to get I2, we come and replace I1 in this expression. Alright, so my I2 is equal to negative x squared e to the negative x plus 2 into I1, and this is I1. But we have the value of I0, it is what we calculated in Roman 1 of the equation. It is negative e to the negative x plus a constant of integration. Alright, so I fit there, and then now the rest is simplification, and then we simplify to get this. So our I2 is negative e to the negative x into x squared plus 2x plus 2, then plus 2k. Remember that we need to specify that k is a real constant. Alright, now the most interesting part of this question is actually Roman 4. It's very interesting because here we are trying to show that a factorial is equal to an integral. So n factorial, this is the definition in terms of integration. So the definition of n factorial is just the integral from 0 to infinity of x to the n e to the negative x dx. Now if you're actually writing this entrance examination and you have taken math as a discipline in year 1 in the university, in any university, I believe you have come across the function called the gamma function. We call it the extended factorial function. It has a similar definition as this. Nevertheless, we dive straight away into what we want to prove. We want to show that the integral from 0 to infinity of x to the n e to the next x dx is equal to n factorial using this concept here. So this integral here, right, what we do is that remember that the integral is not I of n now. Why? Because I of n was the indefinite integral. Now this is a definite integral because we have limits and it is improper. So clearly to get this integral here, it's very simple. I just come to my I of n, right, and I impute the bounds here, because integrating just this function indefinitely is actually integrating is actually I of n. So when I fit limit, I just need to come here and I impute the various limits. So it means that I'm going to get here is negative x to the n e to the negative x, down from 0 to infinity, then plus n times the integral from 0 to infinity of x to the n minus 1 e to the negative x dx. See, I'm not replacing I of n minus 1 there because it is not I of n minus 1. Why? Because I of n minus 1 was an indefinite integral, but here I need to replace it with its equivalent. It's now a definite integral since I have limits from 0 to infinity, and specifically it is an improper integral because infinity is a term, let me put it that way, which is not in the domain of definition of the integrand. Alright, now this is basically we cannot impute infinity by saying negative infinity raised to the power n times e to the negative infinity. No, we don't do that. This is an improper integral, so we need to use the limit definition. Remember, this is a concours, so you don't do things that are absurd. Alright, so maybe if I post my g of n to be equal to this big integral here, Now it means this integral here, right, this is, I'm going to use the limit approach to this. So I'm going to replace infinity here with a constant, and then I look for the limit as that constant is tending to infinity, because infinity is not a real number, you see. So we cannot be inputting infinity into these functions here, and we are expecting to get an answer. We need to take the limit as the variable is tending to infinity. Alright, so maybe if I call the constant to be a, so I replace infinity with a, and then I take the limit as a tends to infinity. I have actually changed nothing. I'll just use the limit definition of that because it is an improper integral. Alright, now here I have my n is constant, but now this here is going to be what? My g of n minus 1, because this is g of n. G of n minus 1, I just replace n with n minus 1. Anyway, I see n in the expression of g of n. Alright, so we need now to look for this limit, but first of all, before doing that, we need to impute the upper and lower limits. Now when we impute 0, which is the lower limit, everything boils down to 0, right? So we just need to impute the upper limit, which is a, and then we find the limit as a tends to plus infinity. Our n g of n minus 1 remains there. Now there is a negative sign here which I missed, so permit me to indicate the negative sign. So I just indicate the negative sign in red. Alright, now look at e to the negative. Remember, I'm now replacing my upper limit, which is a, and then I'm taking the limit as a is tending to plus infinity. So here it's going to give me a to the n because I'm replacing a with x. I'm replacing x with a. So a to the n, the negative sign is outside, then e to the negative a. E to the negative a is the same as 1 over e to the a. This is it. Now I need to compare these two functions, a to the n and e to the a. Clearly e to the a is increasing, that is, it tends faster to infinity than a to the n. It means that everything here is going to tend to 0. So at the end we get the negative sign does not matter. So our g of n, which is the left hand side, will be equal to what? 0 plus n times g of n minus 1. So it means our g of n is equal to n times g of n minus 1. Okay, now how does the factorial function comes about? Because we need to prove that our g of n is equal to n factorial. So the question you should be asking yourself is, what are we going to do to get the factorial function? Alright, have you answered the question? If no, then just follow up what I'm going to do. Alright, so since my g of n is equal to n times g of n minus 1, it means my g of n minus 1 is equal to n minus 1 times g of n minus 2. You just come here, replace n with n minus 1, replace n with n minus 1, and replace n with n minus 1. If I replace n with n minus 1 here, I'm going to get n minus 1, then minus this one to give me n minus 2. So my g of n minus 1 is equal to n minus 1 g of n minus 2. What about g of n minus 2? Is n minus 2 g of n minus 3. What about g of n minus 3? Is n minus 3 g of n minus 4, and so on and so forth. So I'm just going to iterate and get to the last terms. So j2 is equal to 2 times j1, and then j1 is equal to 1 times j0. Alright, what am I going to do now? I'm going to do a backward substitution. So in the place of g of n, I'm going to replace it with n minus 1 times g of n minus 2. In the place of g of n minus 2, I'm going to replace it with n minus 2 times g of n minus 3, and so on and so forth. So you're going to see how the factorial function is going to come about. Alright, so since my g of n was equal to n times g of n minus 1, I replace the value of g of n minus 1, which is n minus 1 times g of n minus 2. Now g of n minus 2, which is in red, I replace it with n minus 2 times g of n minus 3. I replace g of n minus 3 with n minus 3 times g of n minus 4, and so on and so forth. So I continue till I arrive the last term, right, which is 2 times j1, and then now j1 is what? 1 times j0. Now we need to look for the value of j0. But clearly, I hope we are already seeing that we are progressing to the n factorial, because n factorial is n into n minus 1 into n minus 2 into n minus 3 into n minus 4, right, running down till 2 times 1 times 0 factorial. Alright, so we need to look for the value of j0 before we conclude. Okay, so my j0, I just come to jn, I replace n with 0, so I get x raised to the power 0 e to the negative x dx. Alright, so x raised to the power 0 is 1, since x is different from 0. So I get j0 as an integral from 0 to infinity of e to the negative x dx. This is also an improper integral. Nevertheless, when you integrate e to the negative x, you get negative e to the negative x. So we use now the limit definition. So the negative sign is out. The limit as a tends to infinity of e to the negative x is 1 over e to the x. Then you have your limits from 0 to a. Now when you fit the upper limit, you get 1 over e to the a minus, when you fit the lower limit, you get 1 over e to the 0. E to the 0 is 1, so 1 over 1 is 1. Now clearly, as a tends to infinity, e to the a tends to infinity, so 1 over e to the a will be tending to 0. So the interior here gives us 0 minus 1, which is negative 1. We have a negative sign out here which multiplies to give us what? Positive 1. So it means my g0 is equal to 1. So with that said, it means that my g of n is equal to this product right up to what? 2 times 1 times 1. So 1 times 1 is 1. So we get n into n minus 1 into n minus 2 into n minus 3. Write down to 2 times 1. So that indicates the factorial function, which is n factorial. So we can comfortably say that the integral from 0 to infinity of x to the n e to the next x is equal to n factorial, because the integral is g of n. Alright, so guys, if you have an alternative method of approaching the fourth part of this question 1, please, if you can comment, or the comment section is going to be very good, because I believe even mathematical induction can work in this case. You can use mathematical induction to prove this, since we have information about I0, I1 and I2. We can use induction to prove it. Nevertheless, if you enjoyed the video, make sure you like the video, share the video with your friends who are also preparing for the entrance examination. Turn your notifications. For those of you who are not subscribed yet, please endeavor to subscribe to the channel. Alright, so see you in the next video, and I wish you all the best in your entrance examination. Thank you.